So basis sets are specified by usually some sort of acronym, and it becomes somewhat of an alphabet soup if you're not familiar with the terminology that's used. We have things like STO3G, which is one of the most basic basis sets. We get things like 6-311 G star plus, right? And you'll understand what both of these mean. And then there are other more advanced ones, things like augmented polarized valence double zeta basis set. I think the D is usually capitalized as well there. Right, and so without knowing where these come from, it can be very confusing to know which one should you choose if you want to actually do a calculation. So we're going to talk a little bit about, and we'll spend a lot of time talking about these types of basis sets here. So these are known as the Pople basis sets, I guess Pople style basis sets. So the sort of first functional forms that developed to use for computational chemistry were the Slater type orbitals. And one thing I will mention is that with all of these basis sets, when we combine these atomic wave functions, we have to do so in a way that we get antisymmetric wave functions. So we always use Slater determinants. That's kind of built into all of these basis sets, that we use Slater determinants to ensure that we have antisymmetric wave functions with respect to exchange of electrons. So Slater type orbitals are one way of representing this. And the idea here is we could use the hydrogen atom wave functions, but they don't have any variational parameters inside of them. And so we want something that's similar to a hydrogen atom wave function, right? Because we know that the orbitals are going to look something like that, but that we can adjust them, that we have some variational parameters in there. And we looked at an example of a Slater type orbital when we started talking about helium. So it has the same basic functional form. So the actual Slater type orbital has three quantum numbers, N, L, and M. We represent it with spherical coordinates, r, theta, and phi. And there'll be let me look at my notes over here. So I'll just write this as, there's a normalization constant. Then we have r to the n minus 1, e to the minus zeta r, and then we have the spherical harmonics, the ylm, that are angular part of the wave function. So in particular, it's this radial part of the wave function that's a little bit different. And the variational parameters that we have present here, right, are we can vary n, and we can vary zeta, right? That's what this letter is. Okay, so Slater type orbitals are great. They have the right sort of functional form. We have this, negative exponential in the radial part of the wave function. We have this polynomial r to the n minus 1 that shows up. So this would be something, right, that we can represent the different shapes of the orbitals with the the spherical harmonics, the ylm, right? That gives us our s and p and d type orbitals that we're used to seeing. The problem with Slater type orbitals is that they're difficult to use with computers. So we have to compute a lot of integrals, as you've become aware of over the course of the semester. And it's a lot. It's these wave functions of this sort difficult to use in a computer. It's not straightforward to calculate integrals involving these wave functions. And so what we do instead is that a different type of function that's a lot easier to use in computers and to compute integrals especially are Gaussian functions. So in a Gaussian function, we have something that's very similar to a Slater type orbital, so G and Lm. So G here represents Gaussian, and it's going to depend on all of our same parameters here. And we'll have some normalization constant, r to the n minus 1. And the main thing that we change, let me just write that nicely, is that instead of this e to the minus zeta r, we get e to the minus alpha r squared. And this is the Gaussian part of our Gaussian wave functions, because this is known as a Gaussian function. E to the minus x squared is a Gaussian function. And then we still have our spherical harmonics. I accidentally moved that over. Y, Lm, theta, and phi. So we still have our same overall SPDF shaped orbitals, but we've just changed the radial part to include a Gaussian. Now, a Gaussian function doesn't actually represent the real hydrogen atom wave functions as well as the Slater type orbital. And so in the next video, we'll look at how we can use multiple Gaussian functions to represent our Slater type orbitals.